My name is Jacob Hayden. I'm the program coordinator for SaferSim at the University of Iowa. Safety Research Using Simulation, or SaferSim, is a Tier 1 university transportation center with the research priority of promoting safety. Our webinar series features research taking place within our center, and you can see the other institutions involved in our center up on the screen right now. Thank you all for joining us today. Before we get started, I would like to point out the chat box in the Adobe Connect window. Please use this chat box for any questions or comments. There will be time at the end of the presentation for questions and discussion. Now I'm pleased to welcome our presenter from the University of Central Florida, Lishengsa Yu.
Hello, Jacob. Hello, everyone. Next, I will introduce to you about our research project assessing the effectiveness of connected vehicle technologies based on driving simulator experiments. This is the photos of our team members in this project. The connected vehicle technology is expected to reduce crashes and improve road safety. This technology enables the information exchange between a host vehicle and other vehicles and pedestrians. By using the CV technologies, the kinematic information such as braking, acceleration, speed, position, etc. of a vehicle can be transmitted to another vehicle or pedestrian. And if there would be an impending crash risk, the drivers could get a timely notice. Basically, the CV technology reduces the crash risk by improving the driver response behavior. Many studies before show that the connected vehicle technology can result in a shorter reaction time and a larger maximum deceleration. While this influence on driver response behavior might be different between different pre-crash scenarios, because in different scenarios, the crash contributing factors are various, and these factors can be associated with a vehicle and pedestrian speed and trajectory, and associated with other environmental objects such as pedestrian crosswalks and obstructions. The scenario heterogeneities are likely to determine the way a driver perceives the situation's severity and may lead to a different response strategy and safety effectiveness by the CV technology. However, currently, few of research study the difference of CV's effectiveness between scenarios. Therefore, in our project, we aimed to identify such difference. In our project, we focused on pedestrian-to-vehicle, that is P2V technology, and forward collision warning, that is FCW technology. We select these two types of technologies since they are solving the pedestrian crashes and rear-end crashes respectively, which take a significant portion of the total crashes, and they need particular attention. In brief, the P2V technology can send a pedestrian's position and kinematic features to nearby vehicles and alert a driver about an impending collision risk. The FCW technology can alert a driver once he or she failed to keep a safe distance from the leading vehicle. Our study tries to answer two questions. The first question is, how would P2V and forward collision warning technology affect driver response behavior in different pre-crash scenarios? The second question is, how would the safety effectiveness of these two types of technologies vary between different pre-crash scenarios? Our experiment had two parts. One had the pedestrian pre-crash scenarios, and the other one had the rear-end pre-crash scenarios. For pedestrian pre-crash scenarios, we investigated nearly 150 crash reports and analyzed the crash narratives written by the police. From the narratives, we identified the factors and correlated the roadway facility features that contributed to the pedestrian crash. Later, Based on these contributing factors and correlated roadway facility features, we designed these three scenarios. These scenarios simulated real pedestrian crashes caused by two factors. One factor is the obstructed set of view, and the other factor is the failure to recognize pedestrian crossing intention. These two factors take up 40% of total pedestrian crashes. If you want to know more about these numbers and contributing factors, you may refer to our papers shown below, which just comes into publication. Let's look at these three scenarios. In scenario 1, the participant driver is driving in the middle lane at an arterial without a marked pedestrian crosswalk. When the participant passes by the bushes at the roadside, a scenario pedestrian suddenly darts out at 10 miles per hour from behind the bushes. The pedestrian is unobservable before he darts out. In scenario 2, the participant is driving in the middle lane at an arterial without a marked pedestrian crosswalk. A pedestrian is walking along the roadside when the participant is approaching, and the participant doesn't show any obvious evidence that he will cross. The pedestrian is always clearly visible to the participant during the approach. So when the participant driver is close to the pedestrian suddenly darts out to cross the road at 10 miles per hour. In scenario 3, the participant is driving in the rightmost lane at an arterial segment. A pedestrian enters the marked crosswalk from behind a bush. The pedestrian is unobservable until he walks out. We can see that scenario 2 simulates the contributing factor of failure to recognize pedestrian crossing intention, and scenario 1 and 3 simulates the contributing factor of obstructed set of view. This experiment was a within-subject experiment. The warning tag, that is without or with P2V warning, was made as the within variable, and each participant experienced all the three scenarios. The variables we collected include: the first one is the brake reaction time. It specifies the time between the pedestrian entering the road and the time of a participant begins to brake. The smaller the brake reaction time, the earlier the vehicle begins to decelerate. The second variable we collect is the brake transition time. The brake transition time, or brake to maximum brake time, measures the time spent by a driver to reach their maximum deceleration after their initial depression of the brake pedal. A smaller brake transition time indicates a gentle brake. The brake operation time is the total time, it's the sum of the brake reaction time and the brake transition time. Besides these variables, we also collected the braking profile of a driver, and it includes mean and maximum deceleration. For the safety effectiveness, we collect collision rate and post-encroachment time, the PET. The PET is the time difference between the moment a conflict road user leaves the area of a potential collision and the moment of arrival of the other conflict road user. The PET is often used in vehicle pedestrian conflict scenarios as measurement of the safety margin. We had 44 valid participants. These participants were valid because they didn't have motion sickness and followed all the experimental instructions. Among these participants, 25 were males and 19 were females. The average age was 13 years old. The scenarios were presented to each participant in 19 sequence order to account for the carryover effect. This is the experimental results. The first figure is for brake operation time before and after the P2V warning. The second and third figures are for mean deceleration and maximum deceleration. We can see that the P2V warning significantly reduced the brake operation time and increase the braking profile. From the last slide, we know that the P2V improved the driver's response behavior. Therefore, it achieved corresponding safety benefits. Figure 1 shows the change of the collision rate before and after the P2V warning. And Figure 2 is the change of the PET by the warning. We can see that the P2V significantly reduced the collision rate and increased the PET. From previous slides, we can see the change of the driver response behavior and the safety effectiveness resulted by the P2V warning. Well, the results show that this change varies between scenarios. The brake reaction time decreased significantly in all three scenarios, while the scenario 2 was reduced more significantly than scenario 1 and scenario 3. This indicates that in scenario 2, the P2V warning made a driver respond to the danger much faster than before. In scenario 2, the driver observed the pedestrian. However, the drivers didn't think that the pedestrian would cross the road, since the pedestrian was walking along the road without facing the road, without showing any intention to cross the road. Therefore, when the pedestrian suddenly turned into the road, the driver was panicked and couldn't believe their eyes. Consequently, they waited longer to convince themselves until they saw that the pedestrian had really moved a distance. It was this paradoxical tension between what they currently saw and what they originally believed that delayed them to respond. Therefore, as we can see, in the no warning condition, the brake reaction time in scenario 2 was significantly larger than scenario 1 and scenario 3. By providing the P2V warning, the driver got extra evidence to confirm that the pedestrian's crossing intention, and as a result, they could brake faster with less delay. For brake transition time, it increased significantly in scenario 2. However, it didn't change significantly in scenario 1 and scenario 3. This indicates that in scenario 2, the P2V warning enabled the driver to have more gentle brake, which improved the driving comfort. Although the brake operation time and the brake transition time were changed differently by the P2V warning between scenarios, the sum of these two measurements, that is the total brake operation time, had a similar change between scenarios. This was because if a driver started to brake earlier, they were allowed more time to increase the deceleration gradually. In other words, in scenario 2, when there was no P2V warning, the brake strategy was a slow reaction and a hard brake, while the P2V changed the brake strategy to a quick reaction and a gentle brake. For the braking profiles, the P2V warning significantly improved the driver's braking profile in scenario 2. When there was no warning, both the min and max deceleration in scenario 2 was significantly lower than those in scenarios 1 and 3. However, after the warning, the mean deceleration in scenario 2 reached the same deceleration level in scenario 3, and the maximum deceleration in scenario 2 reached the same level in both scenarios 1 and 3. This means that the P2V warning enabled the driver to have a similar braking performance in scenario 2 as that in scenarios 1 and 3. Compared with the huge improvement in driver response behavior in scenario 2, in scenario 3, both the decrease of brake reaction time and the increase of braking profile resulting from the P2V warning was minimum among all the scenarios. This indicates that P2V was less effective in scenario 3. We further combined both the brake operation time and the braking profile together as the response strategy to see how a driver selects different response strategies between scenarios. Different levels of brake operation time and braking profile indicate different patterns of response strategy. And the 4 response strategy patterns were identified by clustering analysis. In cluster 1, a driver immediately moved their foot to the brake when the pedestrian turned into the road. When the driver pressed down on the brake, then the driver pressed down on the brake very quickly and very heavily. Therefore, the response strategy pattern in cluster 1 was labeled as quick, very quick reaction plus very quick and very hard brake. In contrast, cluster 4 had the highest collision rate and the lowest PAT. In cluster 4, a driver initiated braking very late, followed by a slow depression of the brake and a low level of deceleration. Therefore, the response strategy pattern in cluster 4 was labeled as very slow reaction plus slow and gentle brake. Similarly, the response strategy patterns in cluster 2 and cluster 3 were defined like cluster 1 and 4. The results show that in the P2V warning condition, compared with scenarios 1 and 2, more drivers in I need to move to the next slide. More drivers in scenario 3 still select the less safe strategy patterns of cluster 3 and 4. This indicates that in scenario 3, more drivers thought a conservative level of evasive actions would be enough to handle the impending collision risk. Finally, let us look at the safety benefits of the P2V warning between different scenarios. The increase of the PET was the largest in scenario 2, while it was the smallest in scenario 3. Scenario 3 was a low-level risk scenario. In scenario 3, there was a marked crosswalk, and the pedestrian was walking rather than running. The marked crosswalk indicated to the driver that they should be alert for pedestrian crossing in advance, and therefore the walking pedestrian caused less panic for the driver. These features might indicate a low-risk situation. In this type of scenario, both the decrease of the brake reaction time and the increase of the braking profile by the P2V warning were the minimum among all scenarios. Meanwhile, after providing the P2V warning, more drivers in this type of scenario still thought that a conservative evasive action would be enough to handle the impending collision risk. Consequently, the improvement of the safety margin in this type of scenario was the lowest among all scenarios. Compared with scenario 3, the scenario 2 was the most risky scenario. In scenario 2, there was no marked crosswalk. The pedestrian was running rather than walking, and the pedestrian crossing intention was unclear, which caused a confusion for a driver. While the P2V warning might be particularly useful in such scenarios in which a driver had a hard time judging the pedestrian's crossing intention. When there was no P2V warning, this type of scenario had the longest brake reaction time and the lowest deceleration levels. However, by providing the P2V warning, both the brake reaction time and the deceleration was significantly improved more in this scenario than in other types of scenarios. For this type of scenario, the P2V warning enabled the whole braking process to switch from a panic brake of slow reaction and hard brake to a comfortable brake of quick reaction and gentle brake, which indicates a significant improvement in the braking experience. In addition, the results show that after the warning, more drivers in this type of scenario selected a safer response strategy toward the impending collision risk. Further, we conducted a computation simulation to see what is the best warning timing in different pre-crash scenarios. In the experiment, the warning was given 4 seconds before the pedestrian turned into the road. Meanwhile, the speed limit of the driver was set as 45 miles per hour, and the working or running speeds of the pedestrian were constant. Therefore, the safety benefits of the P2V warning obtained from the experiment were only applicable in these specific situations. Essentially, the safety benefit of the P2V warning depends on variations between scenarios such as vehicle's speed, pedestrian speed, and the driver's brake operation time. More importantly, it highly depends on the warning timing. To account for scenario variations and maximize the safety benefit, we used a computation model to identify the best warning timing. The warning timing was defined as the threshold of the time to collision, the TTC, to release the warning. The computation model was defined as like this. We simulated different input variable levels and calculated crash probabilities on the different warning timing. And this is the result. The results show that scenarios 1 and 2 require a larger TTC than scenario 3 to achieve the same level of safety. It indicates that scenarios 1 and 2 are more dangerous than scenario 3. Nevertheless, when the TTC equals 4.5 seconds, almost all crashes can be avoided in all 3 scenarios. Here is the conclusion. The P2V warning reduced the driver's brake operation time and increased the braking profile. Consequently, the collision rate decreased and the safety margin measured by the PET increased. Moreover, the influence of the P2V on both the driver response behavior and the safety effectiveness are dependent on the features of the pre-crash scenarios. In specific, the P2V warning might be particularly useful in pre-crash scenarios in which a driver has a hard time judging the pedestrian's crossing intention, and the P2V warning may be less effective in those low-risk level of pre-crash scenarios. Our computation model shows that even there's a huge heterogeneity between the scenarios, if we set the warning timing to be 4.5 seconds, we can achieve the maximum safety benefits. The second experiment was for the rear end and forward collision warning technologies, and because of the time limitation, we will not go much details for this part. And similar to the pedestrian crash, to the P2V technologies, for the forward collision warning, it was found that the influence of this technology is also dependent on the scenario features. Okay, my presentation is done. Thank you for listening. Any questions or comments?
Thank you, Lishengsa. We do have a few minutes for any questions or comments, as he just mentioned. So we do have a chat box. Feel free to write in any questions or comments there. So we do have a question here from Michelle. A comment from Steve, very interesting, thank you. And then a question from Michelle. Thank you for sharing your work with us. Can you tell us more about how brake reaction time was calculated? I ask because human reaction times are typically no faster than approximately zero point 0.2 seconds, but your results show zero point zero 0.01 and zero point zero 0.05 brake reaction times.
Okay, thank you for your question. Very good point. So we calculate the brake reaction time starts from the time point when the pedestrian enters the road. That means because our warning was given 4 seconds in advance, that means the brake reaction time could be very small when the pedestrian enters the road because the drivers had already prepared for his coming. Do I answer your question? Yes, you're right. The brake reaction time cannot be less than 0.2 seconds. Yeah. But if we calculate the brake reaction time based on the time of the warning release, it will give us a more reasonable results.
Excellent, thank you. We do have a couple other questions. Could you please introduce a bit more about the driving scenarios in your study? For example, the length of each drive, the number of events in each drive,
Okay.
and then can you describe a little bit what the P to V warning looks like in the experiment?
Thank you for the question. The length of each drive lasts for 10 minutes. And we have a 5 minutes break between each driving. The number of events For the number of events, actually there are two critical events in our scenario. The one is with the warning, and the other one without the warning. However, in order to prevent a driver to predict the relationship between particular scenario and the critical events, actually between these two critical events, we arranged similar events between these two critical events. In these similar events, the road facility geometry and the traffic environment were all the same, except that the pedestrian will not cross the road. The P2V warning, what the P2V warning looks like in the experiment. I'm sorry, but I do not put the figure in the slide. So it's a warning icon on the screen, and with a message displaying below the icon, which says pedestrian crossing, please be careful. And besides this visual message, there's also a warning beep. This is what we designed the P2V warning in the experiment.
Thank you. We do have another question that came in. Um, and I guess just a quick follow-up question with that, or to your answer, Lishengsa. So I believe in the final report there are actual images of those pedestrian P2V warnings. That URL is in the flyer, and I'll look to share that in the chat box here shortly. Um, One other question, did you measure the carryover effects? That is, did drivers respond differently for the second and third scenarios that they experienced? And if so, how did their responses change?
Actually, the order of the scenarios presented to the drivers were based on the Latin sequence order, so therefore we consider the carryover effect during the experiment. Each participant will experience the scenarios in different orders. And then finally, we mixed all the results together to make the analysis. No, not already in this study. We will discuss that in the future work. Thank you.
All right, well, thank you for the presentation. I know we are at time. I did just add that URL to the final report. So if you did want to look at those specific warnings or get a little more in depth on this research, please feel free to check that report out. Thank you for your time, everyone. We will have another webinar coming up in 2 weeks. That one will feature research from the University of Wisconsin-Madison and there's research on a machine vision approach for estimating motion discomfort in simulators and self-driving vehicles. So some interesting work coming up. So thank you all for joining. I will send this recording out within the next couple days and look for that future announcement. Thanks, Lishengsa.
Thank you, Jacob.